In this video, we will talk about some of the consequences of the rank nullity theorem. The most important consequence talks about solutions to a system of linear equations. However, before that, let us prove some auxiliary theorems. The first theorem states that if V and W are finite dimensional vector spaces such that dimension of V is greater than dimension of W, then any linear map L from V to W cannot be injective. Let us see a proof of this fact. Notice that L is injective if and only if the null space of L is equal to the singleton set 0. Therefore, we will use the rank nullity theorem and notice that dimension of null space of L is equal to dimension of V minus dimension of range of L. But notice that range of L is a subset of W. Therefore, dimension of range of L is less than or equal to dimension of W. And thus we see that dimension of V minus dimension of range of L is greater than or equal to dimension of V minus dimension of W. In other words, dimension of V minus dimension of W is greater than 0. Thus, the null space of L cannot be equal to the singleton set 0, which implies that L is not injective. And that completes the proof of our theorem. As a consequence of this result, notice that any linear map L from R3 to R2 cannot be injective. Or more generally, notice that any linear map from Rm to Rn cannot be injective if M is greater than N. Finally, we will see a slightly more interesting consequence of this result. Recall, we saw that the derivative map from Pn to Pn minus 1 is linear. And dimension of Pn is strictly greater than dimension of Pn minus 1. Therefore, D is not injective. Now, this is somewhat interesting because we are not really using any other property of derivative. In fact, we are not even using the definition of derivative. All we are using is that derivative is a linear function from Pn to Pn minus 1, and using that we have concluded that there exist distinct functions which has the same derivative. Don't you think that is very interesting? This theorem also has important consequences to solutions to systems of linear equations. For instance, suppose we are given two equations 5x plus 7y plus 3z is equal to 0 and 4x plus 3y is equal to 0. Notice that both these equations, both these linear equations are homogeneous. That means there are no constant terms, and therefore x is equal to 0, y is equal to 0 and z is equal to 0 are certainly solutions. However, we can ask if there is any other solution or not. This especially was important when we wanted to understand linear independence of vectors and things like that. We can of course answer this question by actually solving this system of equations. The second equation will tell you that y is equal to minus 4x by 3. And you can substitute this value of y in the first equation. If you substitute this value of y in the first equation, you will get 5x plus 7 into minus 4 by 3 into x plus 3z is equal to 0. Now this can be simplified as 15x minus 28x plus 9z is equal to 0, which can again be rewritten as minus 13x plus 9z is equal to 0, or z is equal to 13 by 9 into x. Therefore, notice that if you take x to be any value and define y is equal to minus 4 by 3x and z is equal to 13 by 9 into x, then these particular values of x, y and z will be a solution for these two equations. Therefore, we have shown that there exist solutions to this system of linear equations other than the trivial solution 0, 0 and 0. However, the interesting thing is that we could have concluded this without actually solving the linear equations. Let us see how we can do that. Given the system of linear equations, we can consider the function that takes xyz to 5x plus 7y plus 3z, 4x plus 3y. This of course is a linear map from R3 to R2. Therefore, our theorem tells us that null of L is not equal to the singleton set 0. That is, there exists some element x, y, z in the null of L such that x, y, z is not equal to 0, 0, 0. But notice that if x, y, z belongs to the null space, then 5x plus 7y plus 3z, 4x plus 3y is the 0 vector in R2. In other words, it's equal to 0, 0. Or 5x plus 7y plus 3z is equal to 0 and 4x plus 3y is also equal to 0. That is, this particular choice of x, y, z is a solution to the system of linear equations. Therefore, we have proved that there exists a non-trivial solution for this system of linear equations. Of course, there was nothing special about 2. A much more general result is true, and it can be stated as follows. If we have n homogeneous equations in m variables, let those equations be a11 x1 plus a12 x2 plus etc. up to a1m xm is equal to 0, a21 x1 plus a22 x2 plus etc. up to a2m xm is equal to 0, and so on up to an1 x1 plus etc. up to anm xm is equal to 0. Then the system of linear equations will have a non-trivial solution if m is greater than n. By non-trivial solution, I mean a solution where not all xi's are equal to 0. Let us repeat. The theorem states that if you have n homogeneous equations in m variables and m is greater than n, then there exists a non-trivial solution. To prove this, consider a function L from Rm to Rn that takes the vector x1, x2, etc. up to xm to the vector a11 x1 plus etc. up to a1m xm etc. up to an1 x1 plus etc. up to anm xm. Now, as m is strictly greater than n, L cannot be injective. And as L is not injective, we know that the null space of L is not equal to the singleton set 0. That means there is a non-zero vector x1, x2, x3, etc. up to xm that belongs to the null space of L. And those xi's form a solution for this system of linear equations. And as not all xi's are 0, this is a non-trivial solution to the system of linear equations. And thus, the proof of the theorem is complete. Now we will prove a theorem similar to theorem 1, but this time we will take dimension v to be strictly less than dimension w. More precisely, we will show that if v and w are finite dimensional vector spaces such that dimension of v is less than dimension of w, then any linear map L from v to w cannot be surjective. Notice that L is surjective if and only if the range is equal to codomain. In other words, range of L is equal to W. So to show that L is not surjective, we have to show that range of L cannot be equal to W. To show this, once again we use the rank nullity theorem. But rank nullity theorem implies that dimension of range of L is equal to dimension of V minus dimension of the null space of L. But as dimension of null space of L is greater than or equal to 0, this is less than or equal to dimension of V, which is strictly less than dimension of W. Therefore, we know that dimension of range of L is strictly less than dimension of W, or in other words, range of L is not equal to W, which implies that L is not surjective. And thus we have completed the proof of our theorem. As before, we will now see some consequences of this result. The first consequence is that we cannot have a surjective map from Rm to Rn if m is strictly less than n. Another consequence is that the integration map from Pn to Pn plus 1 we saw is linear. Moreover, dimension of Pn is strictly less than dimension of Pn plus 1. Therefore, this map cannot be surjective. Once again, notice that we have used only the linearity of this map and not the definition of integration. And this again is very interesting. Moreover, this might also seem a little surprising. We knew that the derivative map is not injective. To give an example, we know that the derivative of the polynomial x and the derivative of the polynomial x plus 1 are both equal to the polynomial 1. And therefore, the derivative map is not injective. However, this seems a little bit more surprising. Therefore, let us try to understand this a bit better. Let's try to understand which are the functions that do not have a preimage. To do this, we will use the definition of integration, however. So, recall that the integral of 1 is the polynomial x, the integral of the polynomial x is the polynomial x square, and so on. The integral of the polynomial x power n is the polynomial x power n plus 1. Further, notice that the polynomials 1, x, x square, etc. up to x power n form a basis of Pn. Therefore, the range of I will be spanned by the images of these vectors. In other words, we know that range of I is equal to span of x, x square, etc. up to x power n plus 1. Thus, constant polynomials are not there in the range of I. In other words, 1 does not belong to range of I. And more generally, you cannot have polynomials of the form x plus 1 or x square plus 1, etc. So, none of these polynomials are there in range of I. As with theorem 1, theorem 3 also tells us something about solutions to systems of linear equations. Given these polynomials, we can consider a function L from Rm to Rn defined as x1, x2, x3, etc. up to xm is mapped to P1 of x1, x2, etc. up to xm, and so on up to Pn of x1, etc. up to xm. Now this function is linear, therefore if m is strictly less than n, then L is not surjective. In other words, there exists some vector, say c1, c2, etc. up to cn in Rn, such that c1, c2, etc. up to cn does not belong to range of L. In other words, we are saying that if we consider the system of linear equations a11 x1 plus etc. up to a1m xm is equal to c1, etc. up to an1 x1 plus etc. up to anm xm is equal to cn, then we are saying that this system of linear equations will not have a solution. And this is always true whenever m is less than n.